and welcome to Geometry Section 1-2, Inductive Reasoning. There are two different types of reasoning that we talk about in geometry, inductive reasoning and deductive reasoning. Deductive reasoning uses facts, theorems, and properties to draw conclusions. Each step in a deductive reasoning process can be justified with a fact. Inductive reasoning, on the other hand, looks at patterns and then makes assumptions based on those patterns. With inductive reasoning, we're predicting what will happen next, but a lot of times there's no actual proof or evidence to know for certain that our conclusion is right. We have a few basic terms that we use when we're talking about reasoning and logic. The first term is conjecture. A conjecture is an unproven statement based on a pattern or observation. So this is kind of like the hypothesis that you would come up with based on your patterns. It's what you'd expect to happen. Inductive reasoning, like I said before, uses patterns to make conjectures. Another important part of logic and reasoning, and the bane of all conjectures, is the evil counterexample. A counterexample is an example that proves that a conjecture is false, or disproves the conjecture. Let's look at one problem that can be solved using inductive reasoning. In this problem, we're trying to determine the number of handshakes that can take place between 5 people. Hopefully, we'll find a pattern and can then use that pattern to determine the number of handshakes for more people. Let's start with one of the best geometry problem-solving strategies there is, drawing a picture. So we'll start with 2 people. There's only one way those 2 people can shake hands. Now let's add another person. Our original 2 people can still only shake hands one way, but now the third person can shake hands with both of them, so we end up with 3 handshakes total. I don't have quite enough data yet to make a conjecture about 5 handshakes, so let's keep going. With a 4th person, we still have our original 3 handshakes, and now the 4th person can shake hands with the other 3. That brings us up to 6 handshakes total. Can you see a pattern yet? If you can, take a minute to make a conjecture about the number of handshakes for 5 people. Have you got your hypothesis? Let's use our diagram to see if you were right. Adding a 5th person adds 4 more handshakes to our previous 6, making 10 total. Let's use some pattern finding strategies from our last lesson to see if we can find this pattern. The difference between our first 2 terms was 2. The second and third terms differ by 3. The third and fourth terms differ by 4. And the fourth and fifth terms differ by 5. See the pattern now? So, how many handshakes do you think can take place between 6 people? According to my pattern, I should just be adding 5 handshakes to the previous 10. So 5 plus 10 gives me 15 handshakes total for 6 people. Using our diagram, we were able to establish a pattern, and now we can use that pattern to determine the number of handshakes between even more people. How about 10, or 25, or even 100? You probably wouldn't want to draw a diagram for that, and that's why patterns are so important. Now that we've used inductive reasoning to solve a problem, let's review the steps we used to solve that problem. You can use these steps to solve any inductive reasoning problem. First, look for a pattern. To get that pattern, try a few examples and make a table of your results. If you're working with a numerical pattern, it's usually helpful to look at the difference between each term. Next, make your conjecture. You can always change your conjecture later if you find out that it's false. And finally, you'll need to verify your conjecture. This part requires deductive reasoning, and we'll learn that later on in this course. Now let's check out a few example problems. First, let's practice completing some conjectures. To complete a conjecture, it's a good idea to start by testing out a few cases. In the first conjecture, I need to complete the statement, the product of a positive number and a negative number is blank. To finish the statement, we'll test a few products to find a conclusion that fits. So a negative times a positive, let's start with 4 times negative 5. That product equals negative 20. Next, let's try 3 and negative 2. That equals negative 6. It's a good idea to try all kinds of different numbers, so next let's try some fractions. 1/2 times negative 4 is negative 2. 0.25 times negative 6 is negative 1.5. Hopefully now you can draw a conclusion from these examples. Each time we multiply a positive by a negative, our answer is negative. Next, we'll complete the conjecture, the product of an integer, n, and its opposite is blank. For this conjecture, we need to remember what an integer is, as well as the definition of opposites. Integers are positive and negative whole numbers, and an opposite of a number has the same numerical value but the opposite sign. Let's start with 4 and its opposite, negative 4. 4 times negative 4 is negative 16. 5 times its opposite, negative 5, gives us negative 25. Negative 3 times 3 is negative 9. 7 and negative 7 is negative 49. 6 times negative 6 is negative 36. Do you notice anything about all those answers? The most obvious part is that they're all negatives, right? But what do you notice about the numerical parts of the answers? They belong to the set 1, 4, 9, 16, 25, 36, 49, and so on. Do you recognize those? They're perfect squares. So the product of an integer and its opposite is the opposite of the integer squared, or negative n squared. Now let's talk about proving, well, actually disproving conjectures. To prove that a conjecture is true, we have to prove that it's true for all cases. That requires a formal proof. And like I said before, we'll talk about that part later. For now, we're stuck with disproving, but don't worry, this part is fun too, not to mention much easier. To prove that a conjecture is false, we only need to find one counterexample. So we need to find one example where the beginning part of the statement, the hypothesis, is true, but the second part, the conclusion, is false. Counterexamples come in many forms. In our two examples here, we'll be using both numerical counterexamples and visual or pictorial counterexamples. In our first example, we need to disprove the statement, if the sum of two numbers is positive, then the numbers must be positive. So here we're looking for a way to get a positive sum from numbers that aren't both positive. Let's start by choosing a positive sum. How about 6? What are some pairs of numbers we can add together to get 6? 4 and 2, but both of those are positive, so that won't work as a counterexample. 3 and 3, same thing, not a counterexample. Let's try some different types of numbers. How about fractions? 1/2 and 5.5, still both positive, so that won't work either. What about 6 and 0? 0 isn't positive or negative, so it works to disprove the statement. We could also use -2 and 8. Their sum is positive 6, but -2 isn't positive. Remember, it only takes one of those to disprove this conjecture. Now let's look at a more visual conjecture. All shapes with 4 sides are rectangles. Here we need to find a 4-sided figure that's not a rectangle. If you just start drawing some 4-sided figures, I'm sure you'll eventually stumble across something that isn't a rectangle. Here are a few 4-sided figures that I came up with. Can you pick out the ones that work as counterexamples? Each of these could be a counterexample, and remember, it only takes one. That's all for lesson 1-2. Remember, you can rewatch any portion of this video if there were concepts from the lesson that you didn't understand. Thanks for joining me, and happy hypothesizing.